Hi students, you're welcome again to another video of mine, and this is on simple alternating point, or it's a simple AC circuit that is being called. So the purpose of this video series is mainly for revision, and to go video, and my camera is back, and you can see me and see my explanation and details. So we are going to start with the first one. Like I do say, we've done electromagnetic induction. Now we are at AC current or AC circuit, which is a continuation of one of the positive electromagnetic induction that do produce an AC current. Now, when we talk about AC current, it's just like a bidirectional current. As a bidirectional, for the purpose of concept video, they are available on the channel. You can always watch. But this video is just for maximum in-depth of knowledge for minimum words at minimum possible time. So I'm only here to give you a quick revision. So videos are for the sake of quick revision. So let's talk about important thing which I important factor I'm going to talk about in this video. So we start with the first one, ADC. And say this is direct current behind the topic of AC. ADC circuit, in a DC circuit, I guess, maybe had a mistake from the academic team. A 10 microfarad capacitor is placed in series with a 10 ohm resistor. So we have capacitor in series with a 10 ohm resistor, the DC. The total resistance of the combination is that. Now we can say total resistance total will be the resistance of the capacitor, right? That now see of the resistance of the resistor. All right, that has our apologies, guys, for my handwriting. So from here, I can say that so far we have talked about let it be known that the resistance. Let me just give you vital point. The resistance in capacitor or a capacitive circuit. In capacitive, this is hanging. Still waiting for it to come up. Resistance in capacitive, not yet. I think it's back. Capacitive circuit is called the reactance. That is shorty concept, and it is denoted by, it's now called capacitive reactance. It's denoted by NC. It is equals to 1 over omega L, which in junior classes you call omega is 3 pi Fl. We've talked about L yesterday as inductive. Now, which is measuring M. So the same thing is when we talk about instead of omega L, this is omega C. We are talking about capacitor, and this is C. Please excuse me about that. So my point is, in a DC, this is only applicable for alternating current source. In a DC circuit, if you want to get the total resistance, and you want to go by that, the frequency of a DC circuit for this is 10 microfarads. The frequency of a DC circuit is always 0. So what I'm trying to say is that 0 at, because there's no frequency in a resistor in the DC. Sorry, because it is not an alternating source. So if I want to get the SD that is showing here, given 1 over, we can see what I'm saying, 2 times pi multiplied by 0. Why is it 0? Because it is a DC. So all what we're talking about is alternating current source. So a DC doesn't have what an angular frequency or a frequency of flow, but you know, of your reactance or the resistance. So keep that in mind. So basically, I'm saying I have 1 over 0 multiplied by anything. It's 0. So when you divide 1 by 0, you know when the 0 is on that, the answer is what? Infinity of math error. What you see as a syntax error in your calculator. So my point is, infinity is the total resistance which we call reactance in this capacitive circuit. Why? It's because a DC is the one supplying the current, not an AC. So Now, the total one will now be the one in this, which is infinity, plus the one in the resistor was 10. 10 plus infinity is still going to give you infinity. So it's a simple question, but it will not be simple if you don't know the concept. So that's that. So the answer to this question is infinite. From my explanation, I hope students understand this. The second question. Now about the second question, we have a diagram. Diagram not drawn to scale, but I believe you can see it. An alternating current having the waveform. Now, there are different type of alternating current. Let you know. So, but the major one for a level now, I think, is sinusoidal. Sinusoidal waveform, just like we've discussed without waves and oscillation. So it is more or less like the same thing. I don't need to waste your time. We also have rectangular, like I said, alternating currents are always bi-directional. Why do we call them bi-directional? Nature of concept because of time. Time is always a major constraint. So you can see it's move up the positive y-axis and also move down. So if you say current by time, remember Q equals to IT. So say current is equals to the rate of change of that is the Q by dt. In fact, we define current in two ways. We talk about average current. We will not take anything that is more than your level. We'll talk about the other one we call root mean squared for current. This root mean squared current are for the value of we use them under pi. Root mean squared value are used to evaluate powers. We'll talk about the power in an AC segment. I hope you are following this. You have to write something down. So root mean squared, in fact, our level now, you can just keep this in mind. You say the peak value is the maximum current that is flowing at this point for a sinusoidal waveform. It always equals to the root mean square value. Sorry, I said the peak value, the root mean square value. Apology, that is why I derived my formula. For my concept video, you can always watch it. This the root mean square value of current is equals to the peak value divided by square root of 2. So this is derivation available on the watch, but it is not need. You can also say root mean square voltage is equals to the peak voltage. You can see it's moving with a function of time. And because of that, you can also write it as a function of time. For example, the maximum electromotive force is equals to the peak. You can also say sine of omega t. So that is as a time function, which you can write as V as well. And you can also write for current as well as the peak current sine of omega t. These are for the sinusoidal waveform. This is the way this question does not require that, to be honest. The question is a simple question that only asks you for short things, like I just said. So this question says, if x is given by x naught, which is the peak value sine of omega t, which we following is x naught. From what we have studied from our waveform, y is equals to a sine of omega t. So by symmetry, S naught stands for A, which is the amplitude. Where is the amplitude of the waveform? Maximum displacement from the mean position or the equilibrium position. So the maximum displacement from the equilibrium position is what you need. So from here, this is PQ, and the answer to x naught is PQ. The value for this. I hope students understand this. I hope students get this. This is why you have to watch to the year and you have to watch all the videos. So in continuation with that, we'll move to the next slide. Thank you. Now, in the next slide, we have a question in a purely inductive circuit, the current dash. Now, like I said, we have a inductive circuit, though in practice, there's nothing like purely inductive circuit. Inductive circuit. We have a capacitive circuit. And we have one resistance circuit. Resistance circuit. basic thing you just need to know is that most of the time inductive circuit is written as L, C, and this is written as R. Majorly, you guys are used to R, L, C, or any way you write it. All are very correct. But the point I want to make out here for you now, is that whatever it might be, the electromotive force that is being generated, just like electromagnetic induction, we've said that it is what the peak value sine of omega t, it will work for each of them in the same way. So it is from this that we were able to derive the value of the currents too as well. So E is also equals to E naught sine of omega t. A lot of things to be talked about here, to be honest. So if I write also for I, it is written as that. Now we can start from this one because the resistance is just like a normal resistance we've talked about on the electricity, I naught or sine of omega t. So, but when we write for inductive circuit, which we call this is inductant, we represent this one as I naught. You can see what something says sine of the open bracket omega t minus pi by 2. This is the way we write it. And the current here we write as I equals to I naught sine of omega t plus pi by 2. Now, how we come about this? The derivation is available on my channel. It's by what we call phasor analysis, which I think for 11 I don't need to go into derivation. I just need to tell you the application. Now, the meaning of minus pi by 2 means it's current lags. Pi is 180, pi radians 180 divided by 2, that is 180 over 2. So current lags by 90 degrees or by pi by 2. You can see it in any form. Now, here in the capacitive circuit, you can see plus pi by 2. Say current leads by 90 degrees or pi by 2. Whereby here there is no lagging or lead. So this is just the way we interpret. So if we say current lead voltage, here current lags voltage by 90 or voltage lead current by 90. I hope you understand the difference of what I said. So don't make mistake. Now, in this question, inductive circuit, you can see what I talked about. It's lags. The current lags by 90 or voltage leads by 90. This is voltage, which I get is written in some electromagnetic force. So just keep it at the back of your mind. I don't think it should be too difficult for students to get. It's very simple if you are following the lecture. The answer to this is stage, and this is the way we do it. I hope students understand this. The next point we can talk about is the next question. I'll take each question and then I'll be able to explain it to you in details. Now, in an AC circuit, the peak value of the PD is 380 volts. What is the instantaneous PD when the phase angle is 45? Now, phase angle, we are talking about angular velocity. You can see now, circuit, we have talked about PD. I will write PD as V now. You can say V equals to V naught sine alpha, because we are talking about when we know to make an inductive circuit or a capacitive circuit, we are taking it as a resistance circuit. In fact, basically, if I want to draw diagram for you, not phasor analysis diagram, you are not supposed to be scared. All these things are simple, to be honest. It's just because most of you were not taught properly in your secondary schools. That is why you have difficulty here. I got the graph of I told you the resistance in inductive circuit and the capacitive circuit are called reactants. We call them reactants, where it is called resistance in the normal circuit, in the normal resistance circuit. Now, in reactive, we call it reactant, inductive reactant, that is the resistance in an inductor. Capacitive reactants, that is the resistance and the capacitor. I hope students understand the language I'm using. Apologies for my voice. I'm just trying to make sure I finish all as promised. Now, like I said, if we try to draw the value of the reactance against time, you can see for a resistive circuit or resistance circuit, it's going to be something like a straight line because it's not leading or lagging. But you can see this type of question. Like last time, some of my students returned come across graph, and that is why I'm taking my time. Now, like I said, remember I told you here it's lagging, and because of that, we write SL. The formula for that, this is an inductive reactant, is a omega L. I write it like the way you are used to writing it, 2 pi FL, and omega C. XC is a 1 over 2 pi FC, which is the basic formula you have learned in your original classes. And because of that, you can see that the reactant here is increasing. And because it's increasing, the graph is going to be something like an increased graph. This is for resistance. This is increasing, the reactance is increasing with time. So you can say this is for XL, whatever it is. And the other one you can say is inversely proportional to it. Now, when this occurs, you form something like a rectangular hyperbola. I used to tell my students, which you probably guys call mostly inverse, but I will use my hand to draw that. So we have something like this. So, and this is for the SC. So be careful about this type of graph as well. If you are faced with it, I just need to talk about it. I'm going back to my question here. Now we need to understand here that the peak value, which is filling out this 180 sine of the angle, we say sine of omega t plus alpha. So here we are saying sine of alpha because we are not talking in terms of what, in terms of the time function. Please, when we relate in terms of time function, we write omega t. So sine omega t is taken as alpha, which is the angle in this case. So sine of 45. On simplification, you can say 180, I think sine 45 is the same thing as cos 45, which is should be 1 over root 2, not, or you say root 2 over 2, which is better. Sine, I'm doing that a little bit of mathematics. So 2 here, 1, 2 here, 90, it should be 90 root 2. But when my calculation, I hope it is correct, and that should be the correct answer. Yes, it is correct because sine 45 is a true value. So we move to the next question. We are taking it a step at a time. I told you the purpose of this video is for quick revision. The next one says the voltage of the domestic electric supply. Alternating source. We've talked about more and more about it in electromagnetic induction. Most of this light you see, electricity that is supplied to the house, is from the knowledge on the basis of this simple AC segment. Very simple level. Even for advanced level, it is not difficult. So the equation was given as V equals to 311 sine. You can see as a function of time, we can say the same thing as V equals to V naught sine over omega t. I hope students understand. Determine the frequency of this. We've talked about the linear omega. From SHN, we know omega is 2 pi length. So from symmetry, omega here is from symmetry that is setting them equal. Omega here is 314.2. And we know omega formula is 2 pi f is equals to 314.2. On simplification, pi is this. I'm looking for frequency. Frequency will be 314.2 divided by 2 pi. I also understand that I only make up the frequency the subject of the formula. So that is what I need there. So from here, guys, it should give me 314.2 divided by 2 times 3.14. So on simplification, I think it should be A1. It should be A1, right? 100 over 2 should be 50.88, which should be the question answer. So the answer is 50.0, which is the same thing as 50. I hope my students are getting this. And that is the answer for that. We go to the next question. About the next question, we have determined the inductive reactance when 30.0 millihenry. We have to convert. Inductor with negligible resistance is connected to 1.3 times. I think it is 10 raised to power 3. Apologies from the academic team at oscillator. So my dear students, what we'll do here is just the direct formula I've told you. Inductive reactance is written as SL as the resistance of an inductor, which is given as a 2 pi FL. So on simplification, you can say this is 2 times I'll take pi as 3.14 or 142 times the frequency is 1.3 times 10 to the power of 3 multiplied by the look at this now. This is 30 times 10 raised to the power minus 3. And I hope students understand what I have done here. I have only converted. And because I have converted, that is 30 times 10 raised to the power minus 3. You can cancel out this and focus on what you need to focus on. It's so simple to do all these things. I think our simplification distribution was I have calculator here, but I don't like doing that. So I can just multiply all these and see the answer. For my own, I think it should be 1 to 2.5. I'm not that sure. This gets cancelled out. 2 times 30 is 60. 60 times 13. It's very simple to do all these things. Offhand, 780. I'm saying that's 78. 78 times 3. 78. I'm just doing literally 2 stuff. That is 245. I guess it's just a guessing job. Please use your calculator to actually get that. So I think that should be the answer. We can punch your calculator. Like I said, this is just calculator work for you to finish. Now we move to the next step. Fine. Now about the next slide, we have a 120 volt command 60 over pi AC source is connected to a 2 microfarad capacitor. Basically, I still have to convert this one. You remember this is 2 times 10 raised to power negative 6. Like I said, I'm going to give you a lot of work to do here. But these are simple things, and 60 over pi should be the frequency. So note that, and the voltage V is equals to 120 volts. The current passing through this is that. Now let us quickly define an important factor which I think you need to know. If we connect a resistance that inductor coil and with the capacitor, if each of them is connected to an AC supply, the way we do it, just a short concept. I'm not going to waste your time and get straight to the way. Like I said, connected then current will flow normal. You know what I mean by normal. That is just the way I talk sometimes. So when current starts flowing, this is R, L, C. Just keep it in mind. Now, we say the total resistance that is flowing through a circuit. Please listen, the total resistance that is flowing through a circuit, this one has a resistance. The resistance in this is called inductive reactance, and the resistance here is called the capacitive reactance. So the overall, the summation of all the resistance flowing here is now called, we'll define that and we'll call it another time, it's called the impedance, which is denoted by C. Please keep it at the back of the mind. So that is a very good parameter student need to understand. Now, I talked about phasor analysis the other time, or phasor diagram in an AC circuit. It is more like for those of you who understand vectors. I have videos on vectors you can watch, or more like complex numbers in mathematics. Then you have something like a diagram that illustrates. I don't want to waste time. I want to be fast. But one thing about me is that it's look as if I'm not teaching when I don't talk about what is needed to talk. So it's just like your complex number, the way you draw. You remember imaginary numbers and real numbers for students who are math students and real numbers. I'm just trying to show some illustration, nothing more pretentious. So here we have, you say this is now defined as set. So the way you actually talk about it so which you can resolve into magnitude and direction. You know what I mean by that. This is the angle, the direction as a magnitude, and you say direction is maybe I use alpha. So we can also represent, this should be alpha. We can also represent AC circuit in this form, like the magnitude and the direction. Like I said, the whole total, the sum total of all the resistances that is flowing in an RLC circuit or in an AC circuit is called the impedance. So generally it is given as, now in phasor diagram or phasor analysis, there are some basic things you need to keep at the back of your mind, which I think I need to tell you. The electromotive for which is the potential difference is written in form of, always keep it in mind, the peak value then the phasor angle is written as 0 degree. Just for illustration's sake, nothing more potentials. If you write current, the term of the peak current will be the maximum current, is written in form of a particular angle we call phi. For now, keep it at the back of your mind. It's called power factor. I will still explain that. For resistance, if we talk about the peak resistance, the phasor angle is written as still 0 degrees. But this thing as shorty things. Then for SC, SC, we write that one as 1 over omega C or 1 over 2 pi. The phasor angle is saying to be what? Negative pi by 2. So guys, like I said, apologies for the break in transmission. Now, the impedance basically now, from what I have explained thus far, is now given by the factor of Z, trying to make everything very simple and direct. Apologies for the network issue. Yes. Now, Z is now equals to, in terms of, if we want to talk about the phasor analysis, is now equals to the XR plus X. From the phasor analysis that I've given to you, the direction, when you draw a simple line, you're just afraid of the network again. Maybe we are not going to have issues. From what I've given to you, so I told you the R is having the phasor angle of direction of 0, positive axis, so we draw it along this side. Anyhow you want to draw, it's just acceptable. So always keep it is positive. So if you draw, some of you are used to, this is it. Then the other one is drawn, the X can be XL or XC. If it is SL, it is positive, then it will be around this side. Nobody will ask you this, to be honest. I'm just trying. Then you draw the what? The resultant of the two, which is along this. So the resultant of the two is now your Z, which is the sum total of, if I draw like this, then this is what we talked about. This is my XL. If I draw the other one, which is negative, is my SC. But most importantly, questions are not common in phasor analysis. So the angle between the two here is now called, I'll call it alpha. You can say tan alpha is now equals to, say tan theta, mostly it is theta, because when I get to what we call power factor, I'll use alpha. Now tan alpha, no problem, is now XL. And see, this is opposite over, this is the resistance, this is the XL. So XL over R. So this is the interpretation we give to that. This is the direction. So if we go by this also, you can see that the resultant Z is now R squared, which is, if we go by the last formula you guys are used to, you can say Z will now be equals to square root of, from Pythagoras theorem, that is R squared plus SL squared. That is just, and why I'm talking about this is because going forward, if we see a question on it, we'll be able to solve them. So if it is a combination of the L and C, so the impedance is also equals to the sum total to be R squared, then plus you subtract the SL minus SC all squared. I know most of you actually know this formula by heart ordinarily, but you don't know how we come by. So if we talk about E that flow in each of these things, so from what we talk, E is that here is a V equals to I R, the current that is coming, current was supplied, multiplied by R. Here is current. I'm talking about E in each of them, that is the voltage in each of them. I multiplied by SL, and here is an I multiplied by SC. So that is the way we calculate the voltage in each of them. There's the voltage in here, there's the voltage in here. So always keep, so when we now talk about the overall resistance of this connection, we call it what? Impedance. So which is now given in this format. For 3 of them, this is the way we do it. So always keep that. So we can even calculate the total voltage flowing through these 3. We can also keep it in mind. It's important. A lot of things to be kept in mind. So to calculate the total voltage in all these 3 circuits also, you can say it should be the total voltage will be the voltage of the resistant plus that of the inductant plus that of the capacitor. So basically, always keep it in mind as well. If we draw the phasor analysis as well, we are going to have the same thing, which will give us a V, the square root. This is also important. V R square. Then plus we say if it is all the three, it will be VL minus VC all square. This is another important relationship you can also keep in mind to know the overall voltage that is flowing through an LC circuit. So these are shorty concepts you can always know. If it is just ordinary R and C to be S square, the same thing to these two. So keep it in mind at the back of your mind. So if you want to calculate the total current, it will now be I equals to the total voltage divided by the total resistance, which is Z. So this is the way we calculate all that. And we use phasor analysis to also calculate the direction from our knowledge of imaginary numbers or vector analysis we have studied in our junior classes. So I hope students understand that. So now the point is to solve this question, even though I've actually gone a long way. We are calculating the current through the circuit, which is a capacitor. You can see capacitor. So now we can get the capacitive reactance, which is the resistance. SC is of 2 pi FL. Like I said, I've been leaving a lot. So we can say 2 pi, the frequency is in terms of pi, 60 over pi. I said 2 pi FL. It is C, SC, 1 over this 2 pi FC. So I'll put 1 over my stuff here. Apologies, I'm managing the space. I'm sorry about that. So we have 60 over frequency 60 over pi. And this is 2 times 10 raised to 2 times 10 raised to power negative 6, right? So on simplification, pi gets cancelled out. So you can simplify this as 1 over whatever answer you have here. This is 2 times 2 is 4. 4 times 60 is 240. That's 240 times 10 raised to power minus 6. I can just leave my answer like this, which is measuring what? Ohms, because I told you this is resistance. That's the SC. But I'm looking for the current in this circuit. This is the formula, V equals to ISC. So you can make current. Current I will be the voltage passing across it over the SC. So the voltage answer is 120 divided by 1 over 240 times 10 raised to power negative 6. I hope students understand. And our simplification, it will give me a particular answer which you can punch with your calculator. Like I do say, I don't have calculator here, but my workings are always guaranteed because I know as a matter of fact that it will be correct. But all the same, you can as well try it. This is 120 divided by 1 over. So that's 120 times 240, which I believe we can press directly. So I'll be very fast now because there's no time. I'll be leaving a lot for you to solve. This is just calculator one. So one of these answers will surely be the correct answer. So yeah, the next one. The next question says an alternating source is connected in series to a capacitor of capacitive reactance of 10 raised to minus, that is SC. Let's change to a blue. Is equals to 10 raised to power 3 root 3 ohms. Then an resistor of resistance R is 10 raised to power 3. The impedance is what? Direct formula. So it's Z equals to, let's be fast, square root of the resistance that is 10 raised to power 3. Apologies, this thing is hanging. Whenever I'm going to rush you, that is when this is going to run. So we have to increase our pace because I think the network is really giving us issue. 10 raised to power 3, serious issue. You can see the way it is rolling. They're having issues with network seriously. 10 raised to power 3, still waiting for it to come up. All square. Then we say plus the 10 raised to power 3 root 3 all square. If you are not good with how to do this with calculator, you can just how to do this offhand, you can use your calculator. So on simplification, use your calculator. This is 10 raised to power 6 raised to power 3 plus a. This is plus 10 raised to power, we can say root 3 squared is 3. So this is like saying 10, this is 10 raised to power 3 root 3 all squared. 10 raised to power 3 root 3 all squared. It's like saying 10 raised to power, this 10 raised to power 6 times 3. That is it. That is what I have there. So I can write it as 10 raised to 6 or 3 times 10 raised to 6. So you can factorize, then you take the square root. So taking square root of this, you have your answer. My dear student, I am doing this intentionally because now we are now at the level of what? I think the answer to this thing should be, I'm saying option A from what I can see here. Why am I going for option A? Because I can factorize. 10 raised to 6 is common, then I have 1 plus 3. 1 plus 3 is 4. Square root of 4 is 2. So that is 2 times 10 raised to 3. I'm saying 2,000. I think this should be the answer to this. I'm not that sure. Use your calculator to evaluate. What have I done? I can show you, but because of time, I factorize 10 raised to 6 outside. See, 10 raised to 6, open bracket. Although this network is really affecting 1 plus 3 is what I have here. Then we have square root. 1 plus 3 is 4. Square root of 4 is 2. Times 10 raised to 6. Square root of 10 raised to 6 is 10 raised to 3. 2 times 10 raised to 3 is 2,000. That was why I was able to get my answer without calculator. So we'll move to the next one. Now, about the next one, my dear students, we have to calculate the applied voltage in the circuit shown. You can see 3 of them. Like I said, I told you when the 3 are connected, this is from our phasor analysis. This is the direct formula. It will be applied voltage for the 3 of them will be the square root of the 1 for the resistor. You can see 12 squared plus the subtraction of the inductor 8 minus 3. That is 5 squared. I hope students understand. So directly is 144 plus 25. That is 169. Square root of 169 directly is 13. So 13 volts will be the answer to that question. So guys, we don't need to waste our time. We just need to move forward with what we have. So the next one. The next question will be on the next slide. Now I think I need to increase my pace. Now the vector diagram, you can see what I'm talking about. This is just what I drew the other time for you. Shown below represents the resistance R, the capacitive reactance S, C, you can see negative phasor, then inductive reactance S. Oh, there's a typo error. Inductive is SL. So I hope there will be no typo error here too. Oh, there should be type error because I'm seeing the something because the person actually typed the same thing, and the impedance is said the current in the circuit is maximum dash. Now for current, maybe I should just quickly teach you. Keep it in mind. I told you for maximum current, in an RLC circuit, we say the value of R must be equals to Z. What does R stand for? The resistance. Z, it's what? The impedance. So we said for that we have purely reactive or reactive circuit, or purely reactant circuit. That is the way we actually analyze it. Or I said a purely reactant or purely, this is R is resistance, purely resistive. That is the language we say in physics, purely resistive. So when R is equals to Z, we have maximum current. Maximum current also means what we say capacitive reactance is equals to inductive reactance. That's another thing. At that time, we also say we call resonance, the frequency of resonance, which is another important factor you can keep in mind. So for maximum current in an RLC circuit, we say the phasor angle. Another thing, the power factor angle is also equals to 0. Please note that it's equals to 0 degree. So always keep that. We say cos theta. In fact, you can write the cos phi, which is the power factor, is equals to 1. So at that point, SL equals to SE. We have what we define with call the resonance. So in fact, at this time, we can set a formula which is popular. Most of you write it as 1 over, this is the way you see it in my textbook, 2 pi under root of LC. So this is the way you're going to see it. But basically, it is also written here in most of your textbook, 1 over 2 pi root 1 over LC. So at this point, you say SL equals to SC. You say SL minus SC. is equals to 0. From teaching experience, I can tell you most of the thing you need to know. So I told you it's the only way we talk about power factor. The power equals to IV or IE. So IV cos phi. However, the I here we talked about is always the root mean square. I told you the other time. The root mean square value are important in terms of power. So we use root mean square value, then cos phi. So maximum current is when phi is equals to 0 or cos phi equals to 1. Minimum current is when cos phi is equals to 0. Please note that. And at that point, we say the what? It is what? Purely inductive. So don't worry about this. We are just taking with respect to what we have. So my point is the current is maximum. At that point, you have resonance frequency, which SL is equals to S. So here SL equals to SC. This is SC, like I change here. I think there's a typo because it's just repetition. So SL equals to SC. This should be the answer to the question. And at that point, you have resonance. So keep it in mind. That is that. The next one. A series of RLC circuits set to resonate when dash. You can see what I talked about. These are all the conditions for that. So when capacitive reactance is 0 is wrong, conductance is max is wrong, current is minimum is wrong. We have impedance is 0, inductive reactance is 0. Now, when Z equals to R. Now, capacitive reactance, I think this is also a typo again because this should be the correct answer. Current is maximum. So I think it's just a typo. So let's always keep this at the back of our mind. When current is maximum, that is the point you have Z equals to R. And at that point, you can talk about anything else. So this should be maximum current. So please, I think it's a typo from the team. So this is the answer to the question. So please, there is no tendency for mistake not to come about. Apologies for mistake from my team. I think they are actually typing very fast. So note that capacitive reactance is equals to inductive reactance. And at that point, the value of impedance is what? Minimum, low. Conductance is maximum, is not. So current is maximum, is very right. I said R equals to Z. That is the condition. Always keep it at that. R must be equals to Z. And if R is equals to Z, you can follow that. The next question. Now, in an AC diagram above, the resonant frequency is that. We just talked about that. We say at resonance, F naught, the formula is 1 over 2 pi root LC. If you want to use another one, just substitute 1 over 2 pi, answer is in terms of pi, root of L here is 8 times 10 is power minus 3. I've done something like that. And C here is 5 times 10 is power minus 6. I have only converted the values here. And that is what I need. On simplification, this should give me, you can try it on your own, 40 minus 9. That is 32. And this is about 2500 divided by pi. So you can try that. 2500 divided by pi at. You can try that if I'm wrong, but I can't be wrong, especially when I'm using my shortcuts too. But so that's the answer to this. And we move to the next one. So I think this is the last set of questions. I'm going to leave some for you. Look at this. At resonance, the phase angle in AC circuit is, we've talked about this answer. Then this one, the power dissipated in an AC circuit with current of this and voltage of this is that with a phase angle. Now, always keep it in mind. I told you tan theta, this thing is hanging. That is why I have to rush. This is the last set. Apologies, my dear student. Maybe I should leave it for you to do. So I said power factor, power is current times voltage or I square R. Cos of what? Cos of phi. Remember I told you cos phi is used. The current we use is always what? The root mean square. So here you can just substitute. The root mean square was given. And if it is not given, I told you in the beginning of the chapter, root mean square is always the peak over square root of 2. So keep that in mind. So just substitute values. This is 5 times 10 cos 60. So this is 50 times half. That is 25 watts. And that's the answer to that. So always keep it in mind. It's so simple. This cos phi, which we call power factor. always keep in mind, it's also simple. It's given as a, can write it cos phi in case of some other question is r over z. You know, I gave you tan theta or tan alpha. That one is x over r. S can be SL or SC. It's also important formula for some questions you can come across in the future. So note that. The last question, I'll leave this for you guys to solve. More of the same pace, what we've talked about. At resonance frequency F naught, we have 1 over 2 pi root LC. In this question, you are looking for L. Let me see if you can do that. Try these and drop to us in the comment section. So my dear students, this is where I'm going to stop for this section. If you have anything to ask me, you can write a mail to me or drop the comment under that. We have a WhatsApp channel and other channel you can as well join. For full and comprehensive explanation to any question you have, you can have a personal question you want me to solve for you, or you want my team to solve for you. They're always available for you. And like I do say, if you find anything interesting in our video series, consider subscribing. So see you guys soon. Do take care of yourself. Bye for now.